Good day, everyone. I'm Navjeet Singh, and I'm going to present this demonstration of a mock-up project on ML model building. This is a mock-up project, and I have taken the data of combined cycle power plant, which is very easily available on internet. I took it from University of California Machine Learning Dataset Repository. This presentation is intended for predominantly to deal with the managerial aspects a TPM should be concerned with. And so we will be primarily looking at the model building approach through the lens of a PM, and we'll be dealing with the questions that a TPM has to take care and need to be very vigilant about during the entire process. So the intended audience is all the managers and other business stakeholders that are going to be involved in a machine learning solution for any of their business problems. To begin with, we will be following a framework approach. You can take any, but I personally prefer CRISP. It's industry agnostic and anybody can use it. And it links very well with the agile approach of development. Whatever framework you choose, the entire purpose of a framework is to have clear roles and responsibilities defined for the entire team. By team, I mean the stakeholders and other non-technical persons included. Framework helps you to have an order in your approach, and because of the clarity it brings, it helps us save a lot of time and money. We'll not go into the details of CRISP DM. I have given different presentation on that. We'll primarily look at the business understanding and the evaluation aspects here. Most important part is to have business involved in each step, primarily in the business understanding part and evaluating the solution with respect to the business problem. Business understanding is understanding the problem from the user's perspective, what business is trying to resolve. And the evaluation of the model should be done while keeping the business problem in check. Otherwise, the entire purpose of the project will not be solved as expected. A quick comparison where we see that how CRISP deals with the agile framework. In each iteration, we do the complete CRISP. Once a model is developed and trained, we go back to the business, showcase based on the evaluation metrics, how it resolves the problem, is it good enough? Based on the feedback received, we may have to have more data, and more data may bring in new relationships or new understandings. So the entire CRISP is iterated again in a new agile iteration. Remember, at the very beginning, when we try to understand the problem, how clear one may try to explain it, but the systemic view of the problem will emerge gradually. So you're bound to have multiple iterations of your models. Don't try to have the best in the first phase because that is not going to happen. Emergence will actually help you to have a solution that aligns best with the business outcome. Coming back to our problem, we'll take that as an example here. In this combined cycle power plant, we have historic data available. We already know what is to be predicted, and that makes this a supervised regression problem. This is a definition of ML, how this becomes a ML problem. What do we want to do by this is, we want to maximize the efficiency of a power plant. We need to have a plan to mitigate the risks based on the predictions. And the predictions should help us to enhance the maintenance, which means reducing the time taken to maintain it or the money and people required to do that. Or we it may help us to plan upfront. Now we'll move on to the data understanding. Since this is a already cleaned data, this shows here that we do not have any anomalies, no misses. And a close look at the data shows us that there's a very good correlation between ambient temperature and the exhaust vacuum. These are the only 4 features that are available in a data set. And we are also able to see that ambient temperature and the power output are negatively correlated. This is what we can see from a very, our first attempt at data understanding. But if I look closely, I see that the histogram of PE is forming a bimodal characteristic here. This depicts that there could be some hidden seasonality in it. It could be day night, it could be summer and winter, it could be anything. We do not know because we do not have either a date or a time as a feature. So we do not have any missed rows, but we have an entire feature that is missing. And availability of that feature can bring new interpretations, better understanding. This understanding has emerged because of the way we are dealing with the data. As part of this presentation, I bring this problem to the business. Business may be able to bring me the required features. So this is how iteratively my understanding of the problem and the related data will increase with each iteration. Very important aspect is that business has to be part of all the steps and all the iterations. That's how CRISP fits exactly with the agile methodology. Next, we move on to the modeling part. We build a number of small models. The ideal approach is to try to do first attempt based on heuristics so that we can have a baseline. Since this is a linear relationship, so we can try out a linear regression model as well. To help on this bimodality, we try to have a decision tree model because that they help us to break the data into two at every node. So maybe breaking it can help us identify better, or an ensemble where we can put multiple models together. It could be in parallel or series, like we have two decision trees put together in parallel. We put the data into both of them, or maybe we have 20 such trees and put the data into all of them, and then take a weighted mean or a simple mean or any of other methodology you can do to identify the final output. Or this assembly can also be put in a series mode, where the output of one model is fed in as input to the next model. Primarily, we need to have a solution that deals with the business objective. There are various ways to do that. Most important here is the evaluation metrics. If our intention is to have business actually be a key enabler in the evaluation at every step of our part, we need to have an evaluation matrix that is easy for the business to understand, along with the parameters that help us identify the quality of the model. Like we are using average percentage error, which help us compare two models based on the percentage error their prediction is deviating from the true value. And the other metric we are using is R square, which helps us understand the variance that is explained by a given model. We can use root mean square error, but I prefer not to because it helps us to understand how two models can be compared, but it doesn't give a very clear intuition in absolute terms that what does a root mean square error of 2.3 actually means. What is the business impact in terms of dollars or times? It's very difficult to convey that. So now moving on to that part. After running these three models, MLR, DT, and a random forest, we came up with these given R square values here. We clearly see that MLR gives 93% of variance explanation. It is able to help us understand the variance up to 93%. Whereas random forest increases this to 95.4. Clearly, random forest is doing a better prediction, and we can see 0.2%, 0.2% of reduction in the error in percentage terms. But the question here is, which model should we choose? Model performance in terms of output metrics. There are two things. One is the business outcome and another is the model output. These are the evaluation metrics of the model. We are able to compare three models here and we are able to see that random forest is able to explain the variance by 2 percentage points more as compared to MLR. The most important part is to select a model. We need to have some method. We need to have other parameters as well. Cost of running that model, cost of building the model, cost of maintaining that model. Other very important part is that model able to explain me how the prediction is reached? For example, in our one of these three models, the random forest was having 10 estimators, which means there were 10 decision trees put together in parallel to help us build this forest of the trees. And each tree has a depth of 10. 9 in the random forest case, alone it was having a 10th step, 10 nodes over there. The explainability of these three models is in this order. We lose some part of explainability how this particular prediction value with these input parameters is reached. This is the explainable part. If we are not able to explain which factor has contributed how much, we may not be able to fulfill one of our business objectives, which is to plan for risk mitigation or reduce the maintenance costs. If I know how much degrees of temperature change is causing what amount of change in the output in terms of wattage hours, then maybe I am able to manage the temperature and maintain the required power output levels. But if this connection of explainability is lost in by paying the cost of two and by paying this explainability cost and getting the benefit of 2 points in terms of better prediction, then that is not a very safe option to go ahead. because we are losing on the business aspect of the model building. Similarly, operational cost matter. If, let's say, one decision tree with a depth of 10 takes n costs, then a random forest of 10 estimators may add 10 times the latency to the output. It essentially literally means running the model data on 10 trees, which will increase the compute cost as well. In the long run, these costs will pile up. So we have multiple selection parameters here: explaining power, operational cost, prediction quality. Prediction quality is not the supreme item, it is the essential item, but we need to have a complete understanding with the business which parameters are to be weighed how much. Based on these, I have put them in a simple linear order, and I'm saying that why one is bad and why MLR is good here. So based on my initial explanation, I recommend that we should go ahead with the MLR as part of this iteration of the model building. Now this is my matrix to explain it, why we are going with it. This is something that we have to be sure with the business and have to have a clear understanding what is the score we are going to give to each parameter while taking this decision. This is the most important part. We have here only 3 parameters. Maybe after 3 iterations, you will have 30 models to choose from. You cannot go simply by heuristics. You can choose whatever multi-criteria decision modeling methods that you like, maybe ranking order, weightage mean, or AHP, or whatever you wish for. But we have to have a certain method already in place for these list of parameters that we are going to consider to identify the model based on which our recommendations going to hinge on. This is a very simple view. We can have this kind of matrix, or we can have a rank order matrix. Now, based on this, I suggest that we should go ahead with MLR, and I'm clear on my reasons of suggestion. In the next iteration, we can have an ensemble with MLR and a small random forest model. Let's say we need to have this in real time. MLR, due to its less cost, can be put up in the server where it provides real-time predictions. And whenever we are on the edges of our control lines, we may refer to the random forest with the limited data to have the precise prediction, because it is giving predictions 2 points better. This is going to be a combination method that will help us reduce operational expenses, have the explainability power in place, and we will also be able to take benefit of the improved prediction powers of random forest. So these kinds of mix and match methods and techniques can be come up and put it in the production. Coming to the learnings part, 3 primary learnings are: we need to align our evaluation metrics in line with the business expectation of the outcome. Your evaluation metrics should help us resolve the problem, not only deal with the identification of an improved version of a model. Secondly, CRISP works excellent with Agile and is a preferred mode to work with. Simple to understand and does not disturb the associated teams you work with. Most important part, you have to have a model comparison methodology or a framework already put in place before you reach the evaluation. Once your DT team comes up with a number of models, this is the step that's going to confuse you if you do not have a method already in place. It should be quantitative based so that it is easy not only to select the method but doing later iterations to understand how much improvement or where does the new model stands in comparison to the existing ones. If we need to have a change in the business approach, let's say new funds are released for this because of the savings it brings into the environment back to the corporation, then maybe with the enhanced leverage on that budget part, you can look at other models which were not selected prior but now may be eligible. To emphasize on this part, I have specifically added this diagram here that I borrowed from the Google's research paper called Hidden Technical Debt in Machine Learning Systems. It shows that ML model is a tiny part in the entire machine learning setup and infrastructure, which translates into a cost and latency along with this resource management are very significant blocks in the entire system design. So they need to be part of your identification and evaluation. There are other frameworks that help us with these aspects individually. We'll have another presentation for that, which will work on other aspects of ML ops completely. Till then, have these takeaways, and I wish you best for your ML related projects.